Hi, my name is Olashokwemi Martins, and in this video, we're looking at machine learning. So we'll be discussing what machine learning is. We'll look at the concept of machine learning. We'll look at the types. We'll look at the algorithms used in machine learning, and also we'll look at some use cases in Python to understand the context. So machine learning is a subset of artificial intelligence and computer science. Machine learning itself deals with the study and use of data and appropriate algorithms to mimic how humans learn. So what machine learning does is to help the machine, which is the model in this case, to improve on their own accuracy of predicting the possible outcome given some data. So they improve on those accuracy by not being programmed to do so, but by themselves they learn how to improve on the accuracy. Just like how we human beings, how we learn. Over time, we'll learn how to better make better choices over time. So the same way too, machine learning seeks to formulate such into models, whereby the model can over time by itself learn to improve on its own accuracy and make better predictions based on the data which has been presented to it. So in a broader sense, machine learning itself is a practice of getting machines to solve problems by gaining the ability to think. So one will now wonder, why do we need machine learning? Number one is, if you look at the figure that we have here, the first thing here is increase in data generation. These days we are generating a lot of data, particularly on the internet. We have a lot of data, probably on your YouTube, on your Netflix, your email, your WhatsApp, your Facebook. A lot of data is being generated these days, and based on that we can make a lot of decisions based on all of these data. And also, if you look at the manufacturing industry, you take a lot of data, probably the temperature of your machine, the pressure, a whole lot of data that you take. From this data taking, a lot of decisions can be made as regards probably maintenance time and all other things in that manner. So machine learning is very important now because of there's a lot of data that is being generated. Also, machine learning helps us to uncover patterns and trends in data, because if we look at data very well, we can see the trend in data. We can see the patterns by which the data will begin to shape out. So machine learning helps us to uncover these trends and patterns in our data. Also, we use machine learning to solve complex problems, because one thing about intelligence is about solving problems. So we use machine learning to solve complex problems, and also help us make informed decisions. So we make a lot of decisions as human beings, and based on that, machine learning helps us also to make a well-informed decision by going through a lot of data, which might be impossible for the human being to go through by themselves. So here is just showing us the procedure of machine learning. You have your data, you have your machine which you are going to train. The machine in this case is the algorithm that you're training. Then from there you now build a model. After you have built your model, then you now make your predictions. So the term we're going to be familiar with when it comes to machine learning are: one, algorithm, which are the set of rules and statistical techniques that we're going to be using to learn the pattern from data, because machine learning works with data and algorithm. So algorithm itself is the rules and the statistical techniques that we're using to learn the trends or the pattern in the data. Then also model. The model is what we obtain after we have trained the ML algorithm. And also we have what we call the predictor variable. Now the predictor variable in this case is the variable that helps us to make predictions on the output variable that we intend to obtain the predictions for. Now this is what I'm saying. For instance, now if you want to know a person's height, now the height you want to know is the output, which is called the response variable in this case, or the output variable, or the outcome variable in some cases. So the predictor in this case can be the let me say the amount of food that the person is eating. That might help you to predict what the height of that person will be. So predictor variables are variables that helps you to make predictions as it relates to the outcome. So they call them features. So there are features. It might be 1, it might be 2, it might be so many numbers of features that helps you to make prediction on the output variable. And also you have the response variable, which is your output, what you intend to find out, your output. That is your response variable. So the output variable that needs to be predicted by the predictor variable or variables is your response variable. Then from the data you are going to obtain, we always split the data into two, which is the training data and the testing data. So the ML model is built on the training data, while the ML model is now evaluated on the testing data. However, the training and testing data is still from the data you obtained, but I will still show how all of these are done in Python. So these are just the terms that we're going to be discussing when it comes to machine learning. So the process of ML, of machine learning, the process involves two things. Number one is to build a predictive model that can then be used to solve a given problem statement. So here we have just a functional diagram showing the ML process. The first thing is to define the objective, then you gather the data, then you prepare the data, then you do what we call the data exploration, then you build the model, you evaluate your model, then you make predictions. So when it comes to objective definition, the first thing you want to know when you want to define the objective for a machine learning problem is first of all to identify what exactly are you trying to predict. That is the first thing. You need to know what you want to predict. For instance, if it's the maintenance time for a machine that you want to predict, now you need to know that, okay, that is what I want to predict. So that becomes your response variable. In that case, that's the first thing one has to know. That, okay, what am I going to be predicting with my ML model under the definition of the objective? So number two is, what are my target features? What are my predictor variables that will help me in predicting my outcome? For the case of the maintenance that we talked about, it might be the temperature or the pressure that your machine is running on that will help you to make predictions on when to actually do a maintenance on that machine. So you need to know for yourself, what is it that I want to predict as my outcome or my response or my output variable? Then what are the target features? What are my predictor variables I'm going to be using from there? Then what are my input data? So my input data, what are they? Are they temperature or is it pressure? Am I going to use the two together? You know, depending on how the case is. Then what kind of problem is it? Because there are three kinds of problems in machine learning. You have the classification problem, you have the clustering, and you have the regression kind of problem. So how do you know when is classification, when is clustering, when is regression? Now, the kind of data that you want to predict will tell you if it is a binary classification problem or a multi-classification problem, or is clustering or is regression. And this is how you know. For the case of maintenance that we talked about earlier, when it comes to maintenance, it's either you want to maintain or not maintain. So in that case, it's a binary classification problem. It's either you maintain or you don't maintain. So that is what we mean by binary classification. It can either be one of the two. Either you maintain or you don't maintain. But for the case whereby you want to know, for instance, you want to know the number of goals that was scored, you know, in this present World Cup, in that case now, it becomes a regression problem. You know, you want to know, okay, how many goals will be scored? In that case, it's a regression problem. You can't say that's classification. You understand? So that is a kind of regression. Or you want to know a person's weight. That is also regression, because a person's weight will vary from 1 to 2 to 3 to 2.5, you know, 10, 10.1, 60 kg, 60.1, and all of that. That's a regression problem. But in case of clustering is whereby you want to group a set of entities together based on similarity. For instance, if you go to Netflix and you search a particular video or you rent a particular video there, the next time you go there again, some videos that are related to what you have seen before begin to pop up for you as a recommendation. So what they have done in that case is to cluster you in the group of persons that see certain kind of movies on their site. So that is a clustering problem. So those are the things you need to know under definition of the objectives of machine learning. So the next thing is gathering of the data. So number one is, what kind of data do you need? So once you know the problem, you know what you want to predict, you know the target features, you know the input data that you need, you know the kind of problem that it is, then you want to know what kind of data do I need. For instance, if you want to know the person's weight, the data that you might be required to find out is the person's food consumptions, exercises that they do, the kind of work they do, you know, the kind of lifestyle they live. Those are the kind of data you might be needing in that case. If it's the case of the machine maintenance prediction, then you might be looking at the temperature of the machine, you know, the pressure. You might be looking at the viscosity of the oil running in the machine and things like that. And the next thing that you want to know under data gathering is, okay, is this data available? Because once data is not available, then that's the end. You can't do anything, because without the data, there's nothing your ML algorithm can do. So you need to know if the data is available. Now, if data is available, where can I get this data? You know, you need to know where to get those data. Then if you know where to get them, then how can I get it? Because there are some data that probably you might need an approval from probably the owner of the organization or from government. So you need to know how do you get that data, even when you know where to get it. So that is under data gathering. So after then, you want to do what we call data cleaning or preparing your data. Because most times when you get data from whatever source, there will be some inconsistencies in the data. Maybe there are some missing values. Maybe there are some values that they don't just fall in range of the other values that you have. So you might need to get rid of those instances. Then also you might need to transform your data into the desired format that you want. You might get the data in the format that you don't want. For instance, probably you need your data in degrees Celsius and they are giving you the data in Fahrenheit. So in that case, you need to transform it into degrees Celsius that you want. So those are the things that you'll be doing under data cleaning. Then also we'll have what we call the exploratory data analysis. Under the exploratory data analysis, what you want to know is which of the features that you have, you know, has a very high, or let me say a positive relationship with what you want to predict. You know, for instance, if you are looking at, maybe you want to know if it's going to rain on a particular day or not. In that case, you might be getting data like temperature, you might be getting data like humidity, you might be getting data like probably the average temperature in a day, the lowest temperature in a day, and all of that. So, but from all of these features, you need to know which one exactly has the highest significance in terms of predicting your response variable. So that is the place where correlation, you know, comes into play, particularly when it comes to regression problems. You know, regression problems are problems whereby your data outputs, in that case, are continuous data. You know, like a person's weight can be 20, 20.5, 20.8, 30, 30.1, and on and on and on like that. It varies throughout the year based on the lifestyle of the person. So, but for you to know which of the features that you now have has the highest significance in predicting the person's weight, so in that case, you need correlation. And there are three types of correlation. You have the positive correlation, you have the negative, and you have the zero correlation. Now in Python, the pandas library has the correlation class already in it. So you can just use pandas library alongside the correlation class to find correlation in the data. So for positive correlation, you're saying that you have two variables, that the increase in one is equally proportional to increase in the other. So you have two variables, as one increases, the other one equally increase. So that is positive correlation. But for negative, you're saying as one increases, the other decreases. That is for the negative correlation in between two variables. Now for zero correlation, you're saying that if one increase or decrease, nothing happens with the other one, you know. So in that case, it's a zero correlation. For instance, there's no correlation between a person's voice and the person's complexion, you know. There's nothing linking the two together. However, if you look at a person's food consumption in terms of the mass of food they consume and their body weight, you know, that one is positive correlation, because if you eat more, you definitely, you know, gain weight, you know, and all of that. So that is an example of your positive correlation. Then after you have done your experimental data analysis, you want to build a model in this case. And in building the model, what you're trying to say is that you want to build a predictive model at this stage, whereby you are using any of the machine learning algorithms, either your linear regression or your decision tree or your logistic regression, depending on the kind of problem that you have. So, and in this case of building the model, you need to divide your data into two parts, into the training and testing. So you build your model using the training data, and you evaluate your model using the testing data. So that is what you do under building a model. Then model evaluation and optimization. Now, there's no way you would know how well your model has performed if you do not evaluate. So you evaluate your model on the testing data to know how the accuracy of your model is on the testing data. So optimization, on the other hand, what optimization does is a method by which you increase or improve on the performance of your model. So for instance, if you do a model evaluation and you're getting 60% accuracy, in that case, you want to find a method by which you can improve on the accuracy of your model evaluation. Now, that method and the process you are using to do that, to improve on the accuracy of your model, that is what is called optimization. So then when you're done with all of that, then you now make predictions on new data that you don't even have their output before. So you make predictions on new data. So there are three types of ML. You have the supervised learning, you have the unsupervised, and you have the reinforcement learning. So what do we mean by supervised? We mean that you have the data that you have in this case are labeled data. So let me just give an example of what supervised learning is. For instance, if you have a toddler and you want to train that toddler to know how to read ABC, you know, you show the toddler what letter A looks like, and you tell the toddler this is letter A, you know. So in that case, you're showing the data now is letter A, and you're telling the toddler that, okay, this is letter A. You are actually telling the toddler what that data is, what that input is, you know. That is a labeled data. That is supervised learning, whereby you actually are teaching or training the machine using a labeled data. Now, for unsupervised learning, in this case, you're training the machine using an unlabeled data. So you are now allowing the machine itself to, you know, understand the data without supervision. You are not telling the machine what the data is, but you are allowing the machine itself to know that, okay, this is what this data is. So that is unsupervised, just the opposite of your supervised. Then you have the reinforcement learning. So in this case, reinforcement learning is an area of machine learning whereby you have an agent. Now, the agent in this case can be a software, it can be a robot. However, an agent in this case is also the algorithm that you are using on your software or on your robot, in this case, to relate with its environment and learn how to behave in that environment to get a high reward for whatever action is taking in that environment. Let me explain this in human terms. For instance, if you're going from one point to the other and you're in that environment for the first time, you might take several routes to where you're going, and over time in your mind you evaluate that, okay, this is the shortest path to this point that I'm going to, and each time you want to go to that same destination, you always take that shortest path to that destination. What has happened there is that the actions that gave you the best reward in terms of reduced time to your destination, those actions now became a reinforced behavior in you, so that anytime you want to do the same work in that environment, you want to move from that same point to the other in that environment, you always take the shortest path. So those actions that gave you the best reward, that gave the best reward, has been reinforced into you. So that's what reinforcement learning is all about. And also it happens in machine learning, whereby you have an algorithm that you train the algorithm by trial and error, and over time the algorithm learns the best actions to be taken in that environment to get the job done in future time. So that is what reinforcement learning is all about. So here we are just doing a comparison of the three machine learning types that we have. We have the supervised learning, we have the unsupervised, and we have the reinforcement learning. For the definition, we already said that for supervised you use labeled data to train the machine. For the unsupervised, you use unlabeled data to train the machine. For reinforcement, the agent itself, either the algorithm or the software in this case, or the robot in this case, interact with the environment by producing actions and discovers errors or reward based on that action that it has taken. So the kind of problems that you can solve, we already talked about ML problems to be three, which is the regression, clustering, and also the classification problems. So the type of data for supervised is the labeled data. For the unsupervised is the unlabeled data, while for the reinforcement there are no predefined data in this case. So training for the supervised is external supervision, like the case of the toddler we explained. And for the unsupervised, there's no supervision in terms of the training, because the machine itself learns the pattern in the data, learns to understand what the data is. Also for the reinforcement, there's no supervision as well. The approach for supervised learning is that you have a labeled input, which is data in this case. So you map a labeled input onto a known output. But for unsupervised, you understand the pattern and discover the output by yourself. Let me explain this. For instance, if you are getting into an area for the first time, or let me say in a school now, you enter a classroom for the first time, maybe you're the teacher in that class, because of our experiences over time, we tend to believe that those students sitting in front, or probably a student wearing the glasses, are the brilliant ones, and the ones sitting at the back, or probably stopping in the class, are the ones, that are not really doing well in their academics. That might not be the case in most cases, but because of our experience, once we walk in like that, we just look at the students, we look at their conduct, and from there we can begin to group them into different classes, just based on that, without even knowing them from anywhere. So that is an example of unsupervised learning. But for the reinforcement, it's about trial and error method. So like the case of finding your roots in a new environment, like I talked about. For the first time you take a path, it takes you longer to get to where you're going to. Another time again, you take another route. Another time you take another route. Over time, you know the one that gives you the best reward. So that one now becomes the reinforced behavior into you. So each time you want to do the same action again in the environment, the same activity in that environment, you take the same actions that gave you the best reward. So the popular algorithms for supervised learning, you have the linear regression, the logistic regression, you have support vector machine, and the KNN, which is the K nearest neighbor. For the unsupervised, you have the K-means clustering and the C-means clustering. For the reinforcements, you have the Q-learning algorithm. So like we already said, we have three kind of problems in machine learning: the regression, the classification, the clustering. For regression, the kind of learning that you have there is the supervised, and the outputs you have in regression are continuous quantities, like your weight. Your weight keeps changing from 20 today, 20.1 tomorrow, it can be 40 after some weeks, it can be 40.1, it can come down if you come down on your diet and things like that. So that is continuous quantity. The main aim in your regression is to forecast or predict. So for example, you can predict somebody's weight, you can predict the rainfall, you can predict stock market price depending on what you want to predict. And the algorithm for your regression is your linear regression. For classification, we talked about classification problems as problems that can either be a yes or a no. For instance, you want to predict, you want to know if there's going to be rain or not. So is that it rains or it doesn't rain? Or probably you want to know if you are going to maintain a machine or not. Is that you maintain it or you don't maintain it? Those are classification problems, and in that case, that's a binary classification problem anyway, because there are only two classes that you have. But you can have a multi-classification problems whereby you have more than two classes in such instance. So classification problem, the algorithm is also supervised learning, the kind of problem that is supervised learning. Then the output, it's a categorical quantity. So categorical in the sense that it can either be a yes or a no, a true or a false, or even more than two classes that you might have. So the main aim of the classification problem is to compute the category of a data. You want to know the class that data belongs to. So for instance, if you check in your email, you have your inbox, you have your spam. So some mails will go into your email while others will go into your spam. So that is classification problem where machine learning has been used in that case. And the popular algorithm in this case for classification is your logistic regression. Now for the clustering is unsupervised learning. And what you want to do in clustering is to assign data points into clusters. So you just want to assign a data point into a certain cluster based on similarity. Like the case of the Netflix that I used the other time, whereby you search a movie and the next time you go to Netflix, movies that are related to what you searched there before begins to come up as suggestions for you. So that is assigning a data point into clusters. So that is where clustering algorithm has been used in that case. So the main aim in your clustering problem is to group similar items together. We want to group similar items into clusters. So for instance, you want to use that probably in YouTube or in Netflix, like I already explained. And the algorithm in this case is the k-means clustering. So here we have a functional diagram showing the reinforcement learning model. So you have the agent in this case. The agent is tasked to determine whether this is Tom or this is Jerry. So the agent takes some actions in the environment. So you can see the agent, you can see the environment. So the state where the agent is in the environment, so the state is sent to the agent, and also the reward is sent to the agent from the environment. But the agent itself takes actions on the environment. So the agent takes actions on the environment, while the environment sends the state where the agent is in the environment, and also the reward of that state to the agent. So we'll be looking at the algorithms one after the other under the types of machine learning, which is the supervised learning, unsupervised, and the reinforcement learning type. So for the supervised learning algorithms under supervised learning machine learning type, we have the linear regression. So the linear regression is just similar to our normal linear regression, in statistics. And here we have the mathematical model, which is your output y equals your beta naught. Beta naught in this case is your intercept of your regression line on your y-axis plus your beta 1, which is your slope, and your x, which is your feature in this case, and your e, which is the error, which is the distance between the data point and the regression line. So that is what this diagram here is showing. So your y is your dependent variable, your y is your response variable, is your outcome variable in this case, and your x here is your feature, which is your independent variable. So this is your regression line, which has been plotted here. This is your regression line. So this point where this line intercepts with your y is your beta naught, which is your intercept, and the slope of this line is your beta 1. So these are your data points, or this yellow dots are your data points. So the distance from each of them to the regression line is your error, which is what you have in this mathematical model. So I want to show a use case for a linear regression problem in Python. So let me show the data itself. So here I have this data saying that you want to predict the maximum temperature on a particular day. That is what the question is about. That's what you want to predict. That you want to predict the maximum temperature on a certain day. So looking at the question, which is maximum temperature, temperature can vary from whatever number, you know, from probably 30 to 40 to 45 to 50 to 60. So that is telling me that this is a regression problem. You understand? And this is the data already. So the date, the temperature I, the average temperature. So once I know that, okay, what I want to predict is the maximum temperature or whatever it is I want to predict. So that column becomes my response variable column. So this is my response variable column now, because this is what I'm trying to predict. So all these other variables, which is average temperature, low temperature in Fahrenheit, the dew point average, the dew point low, humidity, and all of that I have here now becomes my possible feature, because for linear regression I only want to pick just one feature against this high temperature to predict it. So in that case, I need to find the predictor variable that has the most significant relationship with this high temperature that I want to predict. So I'll just go back to Python and show you. So the first thing you want to do is to import the necessary libraries. So pandas to undo panel data problems, NumPy for numerical analysis, then your matplotlib.pyplot as PLT for data visualization, your Seaborn as SNS also for data visualization. Now from sklearn, sklearn is a library in Python that handles a lot of machine learning problems. So from sklearn.model_selection, I'm importing train, test, split. You recall that we talked about training and testing data. So this is what I'll be using to split my data. Which data am I splitting? This very data into training and testing. So, and I'll be using this train_test_split. So also I need my linear regression model itself. So I'll be getting that also from my sklearn.linear model library. And also I need to import matrices so that I can do my model evaluation and optimization. So that's basically what you do first. So the next thing you want to do is to put in your data. So this is where I have that data saved on my system. This is the path to where the data is. So when I'm using this identifier, data set, so I'm using the pandas library to read that data because it's a CSV file. This file is a CSV file. So I'm using this pandas library to read that CSV file. So here I'm just printing the shape. Shape here will just tell me the number of rows and columns I have in that data. Then this data set.describe just tells me the statistical information about that data. So here it's saying that I have 1319, that's 1319 rows and 21 colon. So this is telling me here, this is my describe, it's telling me the count. If I count, this is the number of rows that I have, which is this. So the mean value, the standard deviation, the mean, minimum, the 25th percentile, the 50th percentile, the 75th percentile, and also the maximum value in these columns that I have there. So this is where I'm doing the correlation I talked about, because once you get your data for linear regression, you already have the question to say, okay, you want to predict the maximum temperature, that's temperature high for a particular day based on the data that you have. So once you know that is what you want to predict, so you want to use correlation to know which should be your X, which is your independent variable. Because if you look at this figure, you have your Y. So my Y in this case is my temperature high. So I want to know what should be my X. So that's what I'm trying to use correlation to find out. So I want to know which of the other features there has the maximum positive significance to my response variable. So in pandas, I already have that correlation class in pandas. So here I see that my data set already is a pandas file, it's in pandas form. So I'm just calling the correlation alongside it. So here I'm seeing a table which is being shown here, telling me my temperature high, average temperature, and temperature low. So if I'm looking at my temperature high as my output, I can see that my average temperature here is 0.97, saying that that is the significance to my high temperature, while by my temperature low is 0.88. So what it's saying is that for every 1 unit increase in temperature low, there will be 0.88 increase in temperature high because it's positive. So but for temperature average, for every 1 unit increase in temperature average, so there will be 0.97 increase on temperature high. So I can see that my temperature average is the one that has the most significance positive to my temperature high. So from there I know that my temperature average would be my X in this case. So this is just showing a figure representation of this same table that you have here. So after that, I'm just visualizing my linear regression here. So I'm plotting my temperature high against temperature average, and we can see that it's about a straight line. So all these are the data points, all these dots that you see are the data points, and we can see that it's almost a perfect straight line. So what linear regression will do now is to plot a straight line in between these data points that will be of equal distance to the farthest data point from this side to this side. So that line will come right at the center here. So, but this is the raw data itself, which is the temperature high against temperature average. So here I'm doing my exploratory data analysis just to see some of the distribution of the data. So here I'm just checking my temperature high, the distribution, and I'm seeing that the highest is probably falling about maybe 90 something here. So just doing that. So this is where I'm splitting my data into training and testing. You know, my X now is my temperature average, which is what I found out using correlation. And from the question, I know that my temperature I is my Y, which is my response variable. So I'm assigning them to X and Y, just as what we have here to X-axis and Y-axis here. So this is where I'm splitting my data. So I'm splitting my temperature average into training and testing, and my temperature I into training and testing. So that's what I'm doing here with this. And I'm saying that my test size is 0.2, that is 20%. That means my training size is 80%. So that's just what I'm saying there. So this is where I'm training my algorithm. So my linear regression model, which I picked from sklearn. So, and I'm calling it against this identifier regressor. So regressor.fit train x train, y train. So what I'm just doing here is saying that plot my linear regression line using my x train data and y train data. So that's just what I'm saying here, that okay, plot my linear regression line on this distribution alone, x train, y train, which is 80% of my original data. So, and I'm saying print my intercept, which is my beta naught, and also print my coefficient, which is my beta 1 in this case. So my intercept here is 9.01, and this is my slope, which is 1.01. So that is what is saying there. So these are making my predictions in this case. So I want to predict using my model. So this regressor now has been trained with the training data using this line here. This is where I trained my regressor. So after then, I'm now using that regressor that I've trained to predict my X test. You know, we split the data into training and testing for both X and Y when we got here at this point, into training and testing for both X and Y. So after I've trained my model using the training of X and Y, so I want to now predict what my Y would be just using my X test alone. So I'm not using my Y test, so I'm only predicting my Y on my X test. So I want to know what my model will predict for my Y based on my X test data. So I'm now going to compare the Y test, which is now the actual, against what my model is predicting for the same instance. So that's what I'm doing using this data frame model here. You know, so all of this line, that's what I'm doing. So this is what I have. The actual, which is my Y test, is this 90, 62, 79, and all of that. So this is what my model is predicting for the same instance. So when the actual is 90, my model is saying 89. When it's a 62, model is saying 65. When it's 79, model is saying 74. When it's 95, model is saying 93, and on like that. So, and this is just a bar graph showing that as well, showing the test, the predicted against the actual. So this is just a bar graph I'm using to show that instance. I'm just plotting the first 25 row. That's what I'm plotting. So this is where I have that. This is head 25. So that's what I'm doing. I'm only plotting the first 25 observations of that. So this is the regression line here that has been plotted on the training and testing. In this case, just to show you the distribution or the testing of X and the testing of Y and the linear regression line that the model has plotted in that instance. So this is where I'm doing my model evaluation in this case. So I'm using my mean absolute error, mean squared error, and root mean squared error, because the problem I'm solving here is a regression problem. So I'm going to be using the error-based criteria to evaluate it. But I can see that my mean absolute error is 2.597, and my mean squared error is 11, and my root mean squared error is 3.35. So these values that I have as my errors to optimize is to find a way to reduce this error. So any method now I'm using to reduce this error from 2.59 into probably 2 or 1 point something is optimization. The same thing goes for my mean squared error and my root mean squared error. So, but here I'm only doing the evaluation. I'm not doing any optimization in this case. So that is what's showing there. So the next algorithm we're looking at is the logistic regression. So for logistic regression is a method of predicting categorical dependent variable. So unlike the linear regression, whereby you only use it for regression problem, in the case of logistic regression, you use the algorithm for classification problem. So you use it to predict categorical dependent variable. So given a set of independent variables in this case. So what you're saying by saying a set of independent variables is that for logistic regression, you can use as many features as possible to predict your response variable. Unlike linear regression, whereby you only use just one feature, one predictor variable. In the case of linear logistic regression, you can use as many independent variable or predictor variable as possible to make your prediction on the response variable. So the kind of problem that you can use your logistic regression for is your binary classification kind of problem. So is that a yes or a no? And this graph here shows what your logistic regression looks like. So it gives you something like a sigmoid curve from 0 to 1. So every value from 0 to 0.49 is taken as 0, while from 0.49 or 0.5 to 1 is taken as 1. So what your logistic regression does is to give you a probability that falls in range of 0 or 1. So that is what your logistic regression does for you. So here is just the model that shows all of that. So actually you can just derive your logistic regression model from your linear regression model. So that's just what has been shown here. So another algorithm is your decision tree. So decision tree is another classification algorithm in supervised learning that can be used to make predictions for categorical variables. So the algorithm looks like your tree, just like an inverted tree. So all this rectangle that you have in them are the datas. So all these lines are what we call decisions, and the final line that you have here, whatever you have in these boxes, is your class. So here we have two classes: on fit, on fit. So, and the question here is just for us to determine if a particular person is fit or not. So whenever we do the tree and we got to where we have just that classes that we want, that is where we have to terminate our tree. So, and that level of your tree is called the leaf node, and the first node where you start your tree from is called the root node, and the nodes in between your root and your leaf are called your intermediate node, and all the lines connecting your nodes are called decisions, or you want to call them branches. So they are called decisions in decision tree. So the major issue in decision tree is to determine which variable or which feature from your data that you have should serve as your root node, because whatever is serving as a root node is the variable or the feature that has the highest significance in predicting your outcome. So to determine which feature should be your root node is the major work in your decision tree. So this is the step to creating your decision tree. So number one is to select the best attributes, like I said, to know which of the data that you have has that significance on the response variable to make it your root node, to make it the first node that you're going to use. So that is number one thing. Then you assign that to the root node. After you determine what that variable should be, assign it to the root node. So for every value of A, you build your descendant nodes, just like what you see here. So this is the root node. So we build the descendant nodes, which are the intermediate node in this case. Then we assign the classes and label the leaf node, which is the final node. So once the classes are correct, then you stop. If the classes are not correct, you iterate over the tree all over again. So the major issue, like I said, is to know what should be your variable in the root node. So I'm going to be explaining that using this data, this small data that we have here. So, and there are two procedures that you would use to determine that from your data. Is what we call the information gain and the entropy. So information gain is the amount of information that a particular feature is giving you concerning the outcome. So any variable that gives you the highest information gain will serve as your variable in the root node, and your entropy is just a way by which you measure the impurity that a certain variable is giving you relating to the outcome. So any variable with high impurity cannot serve as your root node. So once the entropy is high, the information gain will be low, and vice versa. So let's just explain that using this small data here. So we have weather, we have humidity, we have wind, and we have play. And decision 3 here is to classify whether or not a football match should be played. So by the question here saying that we should find out if a football match should be played or not, that automatically sets the colon where we have the play as our response variable colon. So which means the wind, the humidity, and the weather becomes features that we can use to predict whether the match will be played or not. So what we need to know is now which of these features, weather, humidity, or wind, should serve as our root node for the decision 3. So that is where we'll be needing the information gain and the entropy. So we're going to find information gain and entropy for wind, for weather, for wind, and for humidity. So whichever one has the highest information gain and the least impurity will serve as our root node. So to do that, we'll first of all find out the entropy of the parent node. In this case, the parent node is the response variable. That is the play colon is the parent node. So we're going to be looking at what are the outcomes that you have on the parent node. You only have no, yes, no, no. So that means you only have two classes, which is yes or no. So this problem is equally a binary classification problem. So you want to find probability of yes and probability of no. So P yes equals the fraction of yes outcomes in the parent node over the total number of outcomes, and P no is the fraction of no outcomes in the parent node divided by the total number of outcomes in the parent node. If you look at the parent node, which is the play colon here, how many observations do we have? 1, 2, 3, 4. Our rows are our observations and our colons are our variables. So we have 4 observations. So 4 observations, so that means the total number of outcomes is 4, and 4 also here. And for our observations, we have no, no, no. That's 3 no's and 1 yes. So for P yes, that will be 1 over 4, 0.25. And for P no, that will be 3 over 4, 0.75. So to find the entropy, this is the model. So entropy equals minus summation in bracket P yes log base 2 P yes plus P no log base 2 P no. So minus summation in bracket 0.25, that's your P yes, log 2 P yes 0.25 plus 0.75, that's your P no log 2 0.75, which is your P no. So if you do this, you are going to get 0.81125. So that is the entropy in the parent node. So that's the entropy in the parent node, which is 0.81125. Now, the next thing we want to do is to calculate the information gain for the child. Now, once this is the response variable, when you're doing a decision 3, it becomes the parent, and every other colon becomes the child. So we're going to find information gain and entropy for child node weather, information gain and entropy for child node humidity, information gain and entropy for child node wind. So that's what we're going to be doing after we have found the entropy for the parent node. So the entropy of the right side, so for the child node weather, if you look at it, if you create the tree for that, under weather you have sunny, sunny, raining, raining. So when it is sunny, the match was not played. Another time it was sunny, the match was played. When it was raining, the match was not played. When it was raining, the match was not played. So we form a tree. So weather has two variables, sunny or raining. When it was sunny, there were instances where the matches was not played. And when it was sunny, there are other instances where the matches was played. Just what we have seen here. Sunny, no. Sunny, yes. Raining, no. Raining, no. So that means whenever there is rain, the match was not played. So if you look at it, for the child node weather, on the right side, looking at your screen, this is the right side. There is no entropy here. There's no impurity here because whenever it's raining, the match is not played. However, if you look at the left side here of your screen, you see that whenever it's sunny, there are instances where the match was not played. And also whenever it's sunny, there are instances where the match was played. So here there's impurity because you are not sure that, okay, once it's sunny, the match can be played or not played. But you are sure that when it is raining, the match will never be played. So we are going to be finding the entropy of the left side since the right side has no impurity in this case. So PS for the left side will be 1/2 because if you look at it from this data here, sunny is 2. There are 2 times for sunny, 1 instance for no, 1 instance for yes. So that means for yes, 1/2, also for no, 1/2. And the entropy for the left side of the child node weather, just the same formula we used the other time. If you do that, you get an entropy of 1 here. So that's for the left hand side. So we need to now find the summation of the entropy of the child node weather. We only found entropy for the left side. So now I want to know the summation of the entropy of both the left and the right side for the child node. So in that case, we'll be using the number of outcomes in the parent node, which is 4. The total number of outcomes on the left child node, which is 2, no and yes. And total number of outcomes on the right side of the child node weather is 1 here. So that's what we have here. So the weighted average of the entropy, the summation of entropy of both left and right of this child node weather is your number of outcomes in left child node divided by total number of outcomes in the parent node. So that will be 2/4 in this case, times entropy of the left child node plus number of outcomes in the right child node divided by number of outcomes on the parent node times entropy of the right side. And if you recall, the entropy on the right side is 0 because whenever it is raining, the match is not played. So there's no entropy here. That means it's 0. So that is 0 times all of this will be 0. So 0 times all of this will be 0. Then you are left with 2/4 times 1, which is entropy of the left child node, which is 1 here. So that is 2/4 is 0.5. 0.5 times 1 is 0.5. So that is the summation of the entropy of this child node weather is 0.5. So the information gain is entropy of the parent minus the weighted average of the entropy of the children. In this case, the child here is the child node weather and is 0.5. Entropy of the parents, we already got that to be 0.1125. So that will be 0.1125 minus 0.5. That is the information gain of the child node weather is 0.31125. So we'll keep that. That's information gain for that child node. Then we'll move to the child node humidity, doing the same procedure. So we'll do the same procedure for humidity. We can see from the data we have for humidity, once humidity is high, the match is not played. Is high here, is not played. Is high here, is not played. Is normal here, the match was played. So if you build that 3 humidity, you have high. There are 2 classes there, is that high or normal. When it's high, the match is not played. When it's normal, the match was played. From here, we can see that from both sides of humidity, there is no impurity. That means the entropy for both the left and the right is 0, and the summation of entropy also will be 0 for the child node humidity. So the information gain in that case will be entropy of parent minus the weighted average. So that is the entropy of parent is 0.81125 minus 0, which will give you 0.81125. So from here, we know directly that it is humidity that is giving us 100% information gain about whether the match will be played or not. So in this case, humidity will form the root node, and by using the classes that we have in humidity, we got to our final classification, which is the binary classification of either the match was played or not played. So this is the leaf node, this is the root node in this case. So the next algorithm is the random forest. The random forest is just similar to your decision tree, but in this case, you have several trees that forms the forest in this case. So keeping the same procedure for developing a tree in mind, to solve for random forest, there are just some differences. So this is the diagram showing random forest. So you have the data set itself, and from there you have 3 decision trees in this case: decision tree 1, decision tree 2, decision tree 3. So to make predictions based on the random forest, you have to take your new observation through all the trees that you have. So the majority of the class that you are having will now determine the class of that your observation in case of using random forest. So just given here this data, even before then, the advantage of using your random forest is that you achieve more accuracy with random forest compared to decision tree, and also you avoid what we call overfitting and bagging, because when you use decision trees, overfitting now becomes an issue, and also bagging problems in decision tree. So but when you use random forest, you avoid overfitting and bagging problems. So this is the data in this case. You have 4 observations as well, 4 observations, and you have 5 variables. You have here blood flow, you have blocked artery, chest pain is here, weight is here, and heart disease is here. So the question is to predict whether a patient will have heart disease or not. So from that, you know that heart disease is the response variable, is the output variable, and you are going to use this to form a random forest. So the process of random forest is a bit different compared to the decision tree, though you are still going to use the procedure of a decision tree alongside. So the first thing you are going to do is to create a bootstrap of the original data that you have. So how do you create a bootstrap? The first thing you do, you go back to the original data. In this case, there are only 4 observations here. You remove 1 observation and resample another observation. For instance, if I remove this 3rd row, this 3rd observation, then I resample this 4th row in place of this 3rd row which I removed. So that is what has happened here. You can see that we now have abnormal years, 180 years, abnormal years, 180 years, which is resampling this 4th observation in this 3rd observation, whereby I have removed this 3rd observation. That is, so this now becomes the bootstrap of this original data set. So after doing the bootstrap, so from there, I'm going to use the procedure of decision tree to form a decision tree from this bootstrap. So that will be my first decision tree. So again, I will remove another column different from the one I removed before, another row. I can remove here this 2nd row and resample another row there. Then I do another 3. So I'm going to do that 4 times because I have 4 observations. So I'm going to remove the data rows, all the rows one after the other, and resample another row in there. And based on that, I'm going to form 4 decision trees, because I'm going to do a bootstrap 4 times, because I have 4 observations in this case. So from every bootstrap I get, I'll do a decision tree. So in that case, I'm going to have 4 decision trees. So after then, I'm now going to evaluate my model by taking an observation through all the trees, all the 4 trees that I have, and the maximum vote that the observation has from all the trees would be the class of that new observation. So that is the idea about random forest. The only difference is the bootstrapping part. We are still going to use all the ideas that we discussed under decision tree. So another way by which we can test the accuracy of our random forest is that all the observations that we removed when we are doing our bootstrap, we can use those observations that we removed to test our random forest. We can use it to test the accuracy of our random forest. It can serve our testing data for our random forest. So another algorithm we want to look at is the naive Bayes algorithm. So the naive Bayes algorithm is based on the Bayes theorem or probability that we already know. So the naive Bayes algorithm is a supervised learning algorithm used in machine learning to make predictions on supervised learning problems. So, but there's a reason why it is called naive Bayes, why it is called naive. It's called naive because the assumption under naive Bayes is that the features that you have in the data, in the naive Bayes algorithm, the features that you have in the data, they don't have any relationship at all with themselves. So that is why it's called naive. It's saying that the features, they are not in any way related. So that's why it's called naive in this case. So this is the Bayes theorem itself. However, the naive Bayes model is what is shown here, which is P into H slash multiple evidences equals P C1 slash H close bracket P into C2 slash H and all of that onto Pn slash H times PH divided by P multiple evidences. So what are we saying here? The C that we see, all the C1, C2 up until Cn, they are the positive predictor variables, the positive observations that you have. So, and the H are the evidences that you have. But for us to have a better understanding of the naive Bayes, let's just use this small data that we have here. So we have here the observations here is banana, orange, mango, then the total probability of those ones. So we have the type, which is a colon, long, short, sweet, bitter, yellow, then not yellow. So the issue here is to determine a fruit type using the naive Bayes algorithm. So from the data already, we have 3 fruits, which is banana, orange, and mango. So we are given an observation and the type is not there. We have long, we have short, we have sweet, we have bitter, we have yellow, we have not yellow. And we can see that long is true, sweet is true, yellow is true, while others are false. So from there, we know that the positive predictor variables that we have from the observation is long, yellow, and sweet. So that will be C1, C2, and C3 in that case. So, but for us to know this p-value, these p-values are the probability values of those instances, which we are going to get from the data itself. So, to check if this observation, if the fruit type is banana, we need to find probability of it, of this observation being banana. So P banana slash the positive observations, those are the multiple evidences in this case, which is the long, the sweet, and the yellow. So slash long, sweet, and yellow. So what is probability of long? Because long now is C1, sweet is C2, yellow is C3. So if we go back to long, so the probability of long in this total, that's 400 divided by 500, that will give you 0.8. So that's what you have here as 0.8 times the probability of sweet, that's 100 in 500. Sorry, that's 350 in 500 for us. 350 in 650 for sweet, that will give you 0.54. Then for yellow, that is what you have here, that's 450 in 800, that will give you 0.56. And the 0.33 that you see here, because this is times pH. So this pH is probability of banana in all the fruit types that we have. And we have just 3 fruit types. So that banana is 1/3. So 1/3 is 0.333. So if you multiply all of this, divided by P multiple evidences, which is long, sweet, and yellow. So if you multiply all of this, you get 0.809. If we do that also for orange, we'll get 0 in this case, because for C1 orange, if we go back here, C1 orange long is 0/500, so that's 0. So 0 multiplying all of this will give us 0. So for mango, long, sweet, yellow, for mango, we have long, that will be 100/500. Sweet, that will be 150/650. Yellow is 50/800 and 0.33. So multiply all of this, you're going to get 0.0009. So from here, we know that banana has the highest probability of 0.809. So that means banana is the fruit type that naive Bayes is predicting in this case to have this observation. So that is what the method of naive Bayes is all about. So, and here is another algorithm, that is the k nearest neighbor algorithm, which is another supervised learning algorithm in this case. So it's commonly used to classify new data points into target class depending on the feature of its neighboring data point. So from the name k nearest neighbor, so you have data points. So the class of a certain data point is based on the neighbor closest to it, depending on the k number. So the feature of your k nearest neighbor, number 1 is supervised learning algorithm. Number 2 is simple to implement. It is non-parametric because it takes no assumption on the data, and also is a lazy algorithm or a weak algorithm, because either than learning the data, it actually memorizes that data. And in some cases, you can actually use your k nearest neighbor as a regression algorithm, but most cases you find it being used as a classification algorithm. So here is just an instance of a k nearest neighbor showing here. So the k number is number of neighbors that you want to form. So here you have the data points. Some data points are looking like star here. Some data points are looking like triangle. And this square here is the new data point that you want to put in class star or class triangle. So to know the class of this square now depends on the k number, and the k number is the number of neighbor that you are assigning to this data point that you want to know its class. So when you say K3, you're saying that you're taking the 3 closest data points to this new data point. So when K is 3, you know, star and 2 triangles are the closest to this square. So if K is 3, in this case, KNN will classify this square as a triangle. You know, that is why it's called a lazy algorithm. So it's going to classify it as a triangle. However, if you increase the K to 7, like we have done here, now you're going to have 4 stars and 3 triangles. You know, And based on that, KNN will classify this square as a star in this case. So the main issue with K nearest neighbor is how to find the optimal K number for any problem that you might have, and that is where the this elbow method comes in. So the elbow method is a method by which you determine the maximum K number for your K nearest neighbor, or even your K means clustering. You currently use the elbow method to determine the optimal K number so that you can best classify the new data point. So the elbow method is the method that you use to obtain the maximum K number using this model, this summation of squared error, that is sum of squared error. This is SSE, which is summation I equals to 1, then the distance between your data points to the centroid and square. So at the end of the day, you're going to have a graph that looks like this, and where the graph changes course, that point, because the graph always looks like an elbow in this case, so that point where it changes its course, that is the K number that you're going to have. In this case, the K number will be 3. So for this case, the K number will be 3 because if you look at it, the graph here changes course on K3. So these are the possible K numbers, but from this point, you can know that the optimal K is 3. So on the y-axis, you're going to plot the average dispersion as against the K number. So where the K, the graph changes its course, so that point would be your optimal K number. Also in Python, there's a way you can just use some of the class there to just do this easily, which I'll equally show you as we go along. So the next algorithm I'll be checking under supervised learning is the support vector machine. That's the SVM. So the support vector machine is equally a classification algorithm. However, you can equally use it for regression problems. That is the support vector regressor. And you also have the support vector classifier, that's the SVC. So you can either see SVC, support vector classifier, or SVR, which is the support vector regressor. So for the classification, it's called a binary classification algorithm, whereby you can use it to classify a categorical variable. So the method looks quite like this. The feature, the supervised learning algorithm, it's a supervised learning algorithm. So it takes in labeled inputs and determines the output of such data. So you can serve both as regression and classification. I've already talked about that. And it can be used to classify both nonlinear data, which says data that cannot be separated by using a single line as well. So you use the kernel tricks in this case. So what it's saying is that you can use SVC to classify both binary classification problems and multi-classification problems. But in that case of multi-classification problems, you'll be using the kernels of your SVC in Python in this case. So let's assume you have a wolf pack here, and you also have a rabbit on this other side, and you don't want the wolves to eat the rabbit, so you want to build a fence or a wall in between these two packs so that the wolves cannot cross to the rabbit's end, and the rabbit also cannot cross into the wolf class. So this is the fence you have built. So in support vector classifier, this line that divides the two data that you have, this line that divides them, is called the hyperplane. So this hyperplane is equal distance from the closest data to it on both sides. So what you're saying that this hyperplane is not closer to the wolf pack than that of the rabbit pack. So it's always equal distance in between the closest data point from both ends. In this case, the wolf head here and the rabbit head here are the closest data points to this hyperplane. And this hyperplane must fall equidistant from here to here and from here to here. So these two closest data points to this hyperplane on both sides is called the support vectors. So that is why it's called the support vector classifier. So for the, okay, we already explained all of this. So for the nonlinear type of classification, if you look at this problem, you can't have a straight line to separate these red circles and this blue cross that you have here. So in that case, you need to, use the kernel tricks to change them into a 3-dimension. In this case, you cannot have a line that separates them around here. So that is the case of the non-linear kind of instance for your SVC. So I'm going to show a use case in Python whereby we use all the classification algorithm for supervised learning problems that I've talked about. So here is the data set, is the iris data set, if you are familiar with the iris flower. So this is the data set of an iris flower. So you have here 5 variables, which is the septal length, septal width, petal length, petal width, and the variety of iris flower. So the question is to classify the iris flower into the classes that you have. So here, if you look at this, we have the Satosa, that's a class. We have the Versicolor, that's another class. And we also have the Virginica. So we have 3 classes, which is the Satosa, the Versicolor, and we have the Virginica. So those are the 3 classes of iris that we have on this data set. So that means this colon now becomes my response variable colon, while all of this are my features. And because I'm doing a categorical problem using either my logistic regression, support vector machine, k-nearest neighbor, decision tree, or random forest, all of this can be my input features. Unlike linear regression that I have to find one, I can use all the 4 as my predictor variables, and this one is my response variable. So like we did the other time, the first thing is to load all your libraries. Let me just reduce this, I think it's 2. So to load all your libraries, so pandas, numpy, matplotlib, cborn, and SNS for visualization and all of that. For my sklearn, your train test split, because I'm going to train and split you're going to split your data into training and testing. So I'm picking all my classification algorithms, in this case logistic regression from sklearn as well. sklearn.3, I'm picking my decision tree classifier. Also, I'm picking my k-nearest neighbor or my k-neighbors classifier from my sklearn.neighbors. Also, I'm picking my naive bias, my Gaussian naive bias from my sklearn.naive_bias. I'm importing my Gaussian naive bias from there, that's my Gaussian NB. Also my SVC, which is my support vector classifier from my sklearn.svm. Also my random forest classifier from my sklearn.assembles. So my mean mass scalar. Now mean mass scalar is very important when you're dealing with classification problems. I'll tell you why as we go along. So I'm picking that from my sklearn.preprocessing. So for my evaluation for classification algorithms, I'm going to be using the classification report and the confusion metrics. So I'm picking that from my sklearn.matrices for my classification report, and sklearn.matrices, I'm importing from there my confusion metrics. So I'm still going to explain to you the model for confusion metrics later on. So the first thing you're going to do is to bring in your data, just like we did with linear regression. So the data itself, it's a CSV file. So that's why I'm using pandas to read in that file as a CSV file, and I'm storing it into this identifier fruit, and I'm printing the shape just to know the number of row and column, and I'm printing here the first 5 rows. So here I want to know the uniqueness in the variety column, you know, just like what we did here. I want to know the unique entry in this column because I know that this is where I have my class and I want to classify. So this is where I have my class. So I want to know how many classes do I have in this column where I have the classes. So that is what this line is doing. Then I want to group the data, you know, the observation according to the class size under the variety, and I'm doing a count plot just to show that. So here I have 150 rows, 5 colon. If you look at the data, you have septal length, septal width, petal length, petal width, then the variety. So 5 variable, then 150 observation. So the varieties, there are 3: Satosa, versicolor, then virginica. So that's the uniqueness in this column of variety. There are just 3. And under Satosa, versicolor, virginica, there are 50-50 entries, 50-50 observations, which makes 150 observation what you have here, 150,5. So this is the count plot, just plotting the bar graph using the Seaborn library to plot that from the data directly. So for Satosa, versicolor, then the virginica, they are all 50. Just plotting this on this bar graph. So here I'm just doing a box plot just to know what my data looks like. So here is just the box plot, just showing the distribution of the data for the septal length, septal width, petal length, petal width, and also an histogram alongside it. So here is where I'm specifying my X and my Y. So I'm saying here that my X is my variety because that is my class colon. That's my class colon from here, you know, that's my class colon, is my Y, and every other colon becomes my X in this case. So, and I'm saying here my X is my variable, which is my data in this case, and I'm dropping my variety colon. So what I'm just saying is that for my X, don't take this variety colon. So that means my X is this, and this. All the first 4 colon is my X, and my 5th colon is my Y, which is where I have my class. So that's what I'm just trying to specify here. And after here, we are showing the training and test splitting. So I'm equally doing the training and test splitting here. So this is where I'm doing the scaling. This is the min max scaler. Now, 2 things is important: where you are scaling and what you're actually scaling. So you are going to be scaling after you have trained and split your data. You will not scale before. And you are going to be applying your min-max scaler on your X train and your X test. You will not apply your scaling on your Y test or your Y train. So you'll be scaling after you have splitted your data, and you'll be applying your min-max scaler on your training X and testing X alone. Now, what is min-max scaler doing? Min-max scaler is trying to do something. It's trying to ensure that all these entries that you have, they fall between 0 and 1. Because you know, for classification in this case, it's best for you to have your entries in a range that is uniform. Because if you look at it, here I have 5.1, 4.9, Here I have 0.2, 0.4, 0.2, 0.3, 1.7, 3.4. You know, they are not in the same range. So what min-max scaler will do is that to ensure that everything I have on this column will fall between 0 and 1, 0 and 1, 0 and 1, 0 and 1. So they will be on the same scale. So with that, I can have higher accuracy. So I'll be doing that on my X train and Y train. Sorry, on my X train and Y test on these columns alone. This. So that is what my min-max scaling is all about. So after that, I'll be applying my log reg, which is identifier I'm using for my logistic regression. So, and I'm fitting my log reg to my X train and Y train. And I'm printing the accuracy, you know, and I'm printing the classification reports as well. So for my logistic regression on that data, I'm getting an accuracy of 0.9 on the training and 0.89 on the testing. So for my decision tree on the same application, on the same data, I'm getting a accuracy on training 100% and test 0.9%. That's 97% accuracy on testing. So we can see here that decision tree did better to logistic regression, because for my testing I'm getting 97, where log reg is getting 89%. For my k nearest neighbor classifier on my test is getting 97, on training is getting 96. For my naive bias is getting 95 on training, 100% on test. For my SVC, 96% on training, 97 on test. And for my random forest, and I built 1,000 trees in this case. So, and it's getting me 100% on training and 97% on testing. So from all of this, I can see that it is my naive bias classifier that gave me the highest score on test, which is 100%. So that's why I'll be using it for my confusion metrics and my classification report. And you know, I have 3 classes: Virginica, Satosa, and Versicolor. So if this is Satosa, this is Virginica, this is Versicolor. So you can see that you have here 1300, 0160, 009, which means my naive bias classifier classified all the classes on the testing correctly, you know. So that is why you have just one value, the others are 0, 0, 0, 16, 0, 0, 9. So it's telling you that it properly classified, and this is showing me my classification report, my precision, my recall, my F1 score, and my support. So my support is all of this that turn out positive: 13, 16, 9. So 13, 16, and 9. And my accuracy is 100%, you know, 100% accuracy, just what we have here. Just going back to what we have here, 100% accuracy. So we'll discuss what precision is, recall, and F1 score as we go along. So the next algorithm we'll be looking at is the k-means clustering algorithm, and it's under the unsupervised learning algorithm. So the k-means clustering, just similar to your KNN, your k-means clustering will try to cluster a new data point into a certain class based on similarity that such data point has with that class, and is used for unsupervised learning. The k-means is used for unsupervised learning, where your k-nearest neighbor is used for supervised learning. So this process by which objects are classified into a preferred number of groups, so that they are similar, so that they are as dissimilar as possible from one group to the other, but as similar as possible within each group. So like the example I gave initially as to Netflix, or probably you buy something on eBay or Amazon, you know, you use k-means clustering. They have used k-means clustering to cluster you into a group of customers or viewers that view certain movies, or customers that buy certain merchandise from their outfits. So they use a lot of k-means clustering in such cases. And it's unsupervised learning because you don't know anything about the person that is making that entry. But based on whatever the person enters to buy or to view, if it's a movie platform, you have some clusters that you have done saying that whoever says for this kind of film, this is the kind of film that should be showing up for that person subsequently. So that is where k-means clustering has been applied. And here is just showing you the procedure for k-means clustering. So in the case of k-means clustering, the k number is the number of cluster you want to form. Unlike your knn, where your k is number of neighbors that you want the new data points to have, the k in the k-means clustering is the number of clusters you want to form. Also, the problem of ultimate cluster, like the ultimate k number is to the knn, also happens with the k-means clustering. So also the elbow method is commonly used to determine the optimal k number for the k-means in this wise. So this is just showing you the flowchart for k-means clustering. When you start, you assign the number of clusters, which is the number of k that you want to have. So the k now will fall to the centroid of your data point. So, and the centroid must be at the let me say the average distance to all the data points in that cluster. So grouping into a cluster is based on the minimum distance to each centroid that you have created. So what will be happening is that the centroid keeps shifting until it gets to a point whereby is the optimal location in every class. So if you have 2 centroids or 3 centroids, the location of each centroid will be the optimal point it should be to every data point that is associated with that very cluster. So once you arrive to that point, then you end your iteration. So the step is to, number one, the k is the k number, the number of clusters. So you will first of all decide the number of cluster that you want to form, but that one will come from your elbow method to know the cluster that you want to form. Then for every cluster, you choose a centroid. You keep moving your centroid about till you get to the optimal location, just like what the flowchart here is explaining. So I will show a use case in Python whereby k-means clustering has been used. So this is a k-means clustering problem. Then how do we know? The question states that lithium-ion power is the largest provider of electric vehicle, that e-vehicle batteries. So drivers rent batteries typically for a day and then replace it with a charged battery from the company. So lithium power has a variable pricing model based on the driver's driving history. So the lifespan of a battery depends on factors such as overspeeding and the distance driven per driver. So what you need to do is to cluster these drivers based on their battery usage, So from the question, we know that it's an unsupervised learning problem because these drivers, we don't know anything about them really, but yet we need to classify them, into clusters based on their usage of batteries. So let me just show you the data. So here's the data. You have 3 columns. That is the driver ID. That's what the ID here is. Then you have the mean distance a day that the driver covers. And you also have the mean overspeed percent that the driver does per day. Now, if you look at something here, we don't have any colon for the existing group. You know, all along when we're discussing the regression problem with the weather, we have a column where we have the maximum temperature or the high temperature. And also in case of the classification algorithm whereby you are dealing with the iris problem, we have a column for variety where we have the class already. But in this data, we don't have any column for the cluster of driver already. So that tells you that this problem is unsupervised in this case, because the output you want to get, the cluster you want to have, you don't have any information about it to start with. So it is the model that will now look at this data by itself to know what class I'm going to fit in these drivers with these IDs eventually. So let's go back to Python. So you import your libraries. So in this case, NumPy, Pandas, Matplotlib, Seaborn and SNS. Also from sklearn.cluster, here we import the k-means in this case. So the first thing you're going to do again is to load your data like we have always done, because the data is a CSV file, and this is the path to where I have the data on my system. And I'm using the Pandas library to read this CSV file, and I'm storing it into this identifier data. And I'm just using the describe here to see the statistical status of the data. And here this shape is just to show me number of column and row of my data. So this is my describe showing me the counts. So I have 4,000 entries. So 4,000 entries is what I have. The mean value is this on these two columns for mean distance per day that driver covers, and the mean over speed percent. So that are the minimum and the mean value. This is standard deviation. This is the minimum value. This is the 25th percentile, 50th, 75th, and the maximum value in those columns. So I have 4,000 rows and 3 columns. So 4,000 observations and 3 columns, which means I have 3 variables and 4,000 observations. So 4,000 drivers. So that's what it means that I have. So I'm just showing here the first 5 rows. If you look at this, you'll see that this is exactly what I have here. 71.24, 28, 52.53, 25. This is the first 5 rows that I have in that data. That's what I'm showing here. So what I'm doing here is just to look at my data. If I have any null values there, if I have any 0, because 4,000 observation is difficult for me to go through myself. So I'm using Python to look at this data, look at the info of that data, and tell me if I have any blank space there. But I can see from the columns I have on my ID column, the null values, there are none. For my mean distance per day, there are none. For my mean over speed per day percent, there are none. So that means there is no blank space in that 4,000 observations that I have. So you can see here the sum of is null. There are 0 sum because there's no null values there. So I'm just printing a heat map here just to show me if I have null values as well. So since my heat map is one color, if there are null values, those ones will be dotted in black. So because there are no such thing here, it tells me that there are no null value in this data. So the data is clean. That's what it's saying. So what I want to do now is to assign my X. In this case, I don't have any Y because it's unsupervised. So I only have X. So I'll be using these 2 columns for my X, and my model will find out what my group should be for those drivers. So I'm assigning row 1 and 2. Column 1 and 2 and all the rows there, all the values there to X, and I'm printing the shape. You can see that the shape is 4,000 in this case. So here's where I'm trying to determine my optimal K number using my elbow method. So in Python, there's a way we do that for I in range of 1 to 11. So majorly we'll choose our K number between 1 and 10. So for I in range of 1, 11, because using the range function, 1 to 11 will give me 1 to 10. So that's what I'm trying to do here to know my optimal K number. So I'm visualizing that elbow method here, and I can see from this elbow method here, I can see that this is where my curve changes. So which means my optimal K number is 2 in this case. So my optimal K number is 2 in this case. So I'm going to use 2. So that is why you see here that I'm saying my n underscore cluster is 2, because my optimal K number is 2. So I'm forming just 2 clusters. So after all of that, I'm going to print my clusters, and let's see where the drivers will be assigned. So we can see the centroid is 0 and 1 because there are 2 clusters. So 2 clusters, 0. Cluster 0 is 0 is cluster 1, while centroid 1 is cluster 2. So if you visualize this, so this is what we have. So we have 2 clusters. This is the centroid for this cluster, and this is the centroid for this cluster. So cluster 1 and 2, cluster 2 is blue, cluster 1 is red, and the centroid is yellow. So that's what we have here, what we are visualizing here. So mean over speed percent here, and mean distance per day here. So what is this telling us? It's telling us that the drivers in this cluster, they are drivers that are covering a minimum distance of 50 units, and their overspeed is 60 on the average per day. So, and here, these drivers, their overspeed is going as high as 100, and they are covering about, if they are using the centroid, they are covering about 180 distance units per day. So what the company wants to know is which of these clusters are using the battery better. From here, you can see that it is the drivers here that are using the battery better because they are not covering too much distance and they are not overspeeding. So their own batteries will not have lost as much charge that the customers here would have lost on their own battery. The customers in this blue cluster, they will use their battery more because they overspeed more and they cover more distance. So what the company wants to do is to know how to charge their customers. So any driver that falls into this category of blue clusters, they will charge them more, while the ones in this red category will be charged less. So from there, the company will make more profits, because the whole idea is the company wants to make more profit by knowing how to price, how to actually bill their clients that come to pick up charge battery from their stores. So they will charge the drivers that fall into this category more because they use their battery more compared to the ones that fall into this category. So that is one application of your K-means clustering that we have seen. So now I'll be talking about the performance evaluation of these algorithms. You know, we talked about regression and classification problems and clustering problems. For unsupervised, you don't evaluate, because if you look at the K-means clustering that I showed earlier, we didn't evaluate because we don't have the actual class to now say we want to evaluate it against what the model is predicting. So there's no way we want to evaluate that. But for the regression, whereby we have used the linear regression, or the classification problems where we have used the classification algorithms, when the problems are supervised, so we can actually evaluate. So there are two methods by which we can evaluate. Is that we are using the error-based, or we are using the confusion matrix method. So when do we use the error-based? When do we use the confusion matrix method? The error-based is for regression problems, while the confusion matrix is for the classification problems. So for the error-based, we have the mean absolute error, just like what we saw when we're doing the linear regression, the mean absolute error. This is the mean absolute error. For the classification is where we have the confusion matrix that we saw here. So the mean absolute error, we have the mean squared error, we have the root mean squared error, just what we have used here: mean absolute error, mean squared error, and the root mean squared error. So these are the models. This is what the system used. So 1 over n summation ni equals 1 into xi minus oi. So what is just saying, and the absolute value of that, your xi is your actual, while your oi is your predicted. So this is what the model did. Here, this is the actual, this is my xi, this is my oi. So this minus this, 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 this minus this. So the magnitude of the difference of each instances, that is the xi minus oi, xi minus oi, xi minus oi, xi minus oi. So the magnitude of those distances, the summation of it divided by the number of observations, that is the mean absolute error. So xi minus oi, the summation of all the magnitude of the differences divided by the number of observations that you have, 1 over n. So for the mean squared error, it's just the same thing, xi minus oi squared. So the difference of all the instances of the actual and the predicted, the summation of it, the square of those differences, the summation of it divided by the number of observation, that is the mean squared error. The root mean squared error is just the same thing, just the square root of your mean squared error is your root mean squared error. Just what you have here, xi minus oi, actual minus predicted, square the difference of those instances, summation of all the instances divided by the observation, then find the square root of it. So that is how the model got all these values from. This is what you have. So that is for the error based. And the accuracy in this case, to determine the accuracy, your accuracy is your error rate minus, error rate equals the absolute into experimental value minus theoretical value. Just saying the absolute value of your xi minus oi divided by your theoretical value, which is your absolute in this case, which is your actual. So actual minus predicted divided by predicted. But the difference between actual and predicted, you are taking the absolute value, the magnitude of that difference. So for every instance here, this minus this, the absolute value divided by the actual 90. So that of 90 minus this 9 point this divided by 90, that is number 1, the first instance, on and on till the last observation. Then you do this maths for it, then multiply it by 100. Then your accuracy is now 100%, 100 minus the error rate that you got. At the end of the day, you sum all of that together and you now get the accuracy. So the closer your accuracy is to 100, the better your model is doing. And the farther from 100, the less effective your model is performing. The other method for evaluation, which is the confusion metrics method, is the method by which you evaluate a classification algorithm. For regression problems, you use error-based, whereby for classification problems, you use the confusion metrics. So in the case of confusion metrics, you already have the class of the data already because they are for supervised learning problems. So here you have the actual data, you have the predicted. Now you have two classes in this case. This is a binary classification problem. You have good, you have bad for the actual class. Predicted also, you have good, you have bad. So your model is one predicting. From the data, you have the actual value as good as bad and as good and bad. So what you have here, true positive, false negative, false positive, and true negative. Now, actual, you have good here. Predicted, you have good here. So whatever value you have here is falling under good for predicted and good for actual. So that means your model predicted whatever value you have here correctly as it relates to the actual, what you have here. But this is bad. This is false negative. On the observation for actual is under good, which implies whatever value you have here, your model has predicted it wrongly because it's actually good, but your model is saying it's bad. That is why it is false negative. Now for the bad row on the actual, false positive here, predicted here is saying good. So predicted is saying this value are good, whereby actually they are bad. So that is why it is called false positive. But here you have bad and equally bad here. So whatever value you have here are true negative because your model is predicting them as bad and actually they are bad. So that is the true negative. So you have true positive here, true negative here, false negative here, and false positive here. So I'm just using an analogy here for gender classification problem. So actual, you have male, female, and you have predicted or predictions, you have male and female. So here you have true positive, true negative, false negative, false positive. And your confusion matrix equals your true positive plus true negative divided by your true positive plus true negative plus false positive plus false negative. So that's how you find your confusion matrix. So if we go back to the classification problem here, this is the confusion matrix report, you know. So everything you have on this diagonal are your true positive and true negative, because if you check this, you see that the positives are on the diagonal. You check this, they're on the diagonal. So like we already said, for reinforcement learning, it's about training an algorithm. Probably you want to use the algorithm in the software, or you want to use the algorithm in a robot, such that that algorithm learns how to take the best actions that will give the algorithm the best reward, because reinforcement learning is about actions and rewards. So you train an algorithm, you know, by that algorithm taking actions by trial and error to see what reward am I going to be getting. So those actions that gives it higher reward are the actions that gets reinforced into that algorithm that you are training, such that when the algorithm wants to carry out that same activity again, it just directly takes those best actions, you know. And here is just a functional diagram showing that. So you have here the environment, that's where the algorithm is operating. Here the algorithm is on a robot here, and the reinforcing signal is from the environment into the algorithm, because that is the reward it's getting. So the agent itself takes actions on the environment, and the environment sends the state, which is the current space that the agent is in the environment, to the agent from the environment. So what the agent wants to do is to be at the best state, which is his own goal state, where it is going to in that environment. So it's taking actions that will take it to that goal state and checking how these actions are rewarding it. So the ones that gives it the highest reward in getting to the goal state are the actions, or the series of actions that the agents will be taking. In this case, is the algorithm that is doing the learning, not the robot in this case, because what you have on your robot is the algorithm, not the hardware that is doing the learning. It's the algorithm that you have. So the terms that you'll be familiar with when it comes to reinforcement learning is the agent, which is the reinforcement learning algorithm in this case, which is learning through the trial and error. The environment is where the agent is moving, where it is actually doing the work. Then actions, the possible steps that the agent can take. Then the state, the current conditions that will be returned from the environment to the agents. Then the reward, the instant reward, the environment is, appraising the action, the last action the agent took. The environment will appraise it and send the reward to the agent. And also the policy. The policy is the approach by which the agent is using to determine the next action based on the current state. Then the value V is the expected long-term reward, or the long-term return with discount, as opposed to the short-term reward R. And also the action value Q is similar to the value V, except that it takes in extra parameter, which is the current action A. So the model that is used in your reinforcement learning is the Markov decision process. That's MDP. That's mathematical model that is being used. And the popular algorithm. Okay, let's just look at this node analysis. So for here we have A, B, C, D, and E, and this part that you have and the value you have here are the cost for the robots to take this part, for the algorithm to take this part. These are the costs. So the question here is for the agent to find the shortest path from A to E with the minimum possible cost. So the agent wants to move from A to E with the minimum possible cost. So if the agent goes from A to B, that's minus 10. From B to E, so that's minus 10 plus 40, that will be 30. That will be the cost of 40. But if it goes from A to C to E, that will be A to C, that will be 15. 15 minus 5 will get it to E, that will be 10. And also if it goes from A to B to C to E, all of those. But the optimal path that will give it the minimum cost is from A to C to E, which is what is taken here. So the policy is now the path taken to get to that destination. So the reward is what you have. All these values are the reward of taking each of these, paths for the robot. So the most common algorithm in your reinforcement learning is the Q-learning algorithm, and the model is this: your Q into state, action equals your R into state, action plus gamma multiplied by max into Q next state, all actions. So I will explain this also in the next frame. So here you have a floor map of a floor plan of a certain building, and you have here rooms, and these rooms have been given node 0, node 1, node 4, node 3, node 2, and outside of the floor plan is node 5. So anywhere outside all the rooms is node 5. So to use Q-learning algorithm to know the best path to take in this environment, because we have been told here that the destination is 5, which is outside this building, outside this floor plan, which is 5 is the destination. So what the agent wants to learn is how to move from any of these nodes, the best path to take to 5. That is what the agent wants to learn. So the first thing that would need to be done is to convert this map into what we call the node equivalent of it. So here I have all the nodes 0, 1, 3, 4, 2, and 5. So these arrows are showing nodes that are linked together. So if you look at it, 2 is linked to 3. If you look at it here, I can move from 2 to 3 back and forth. So that's why you have 2 arrows here, 2 to 3. I can equally move from 1 to 5 back and forth, 1 to 5 back and forth. So 1 to 5 back and forth. So from 3 to 1 also back and forth, I can move. This is room 3, this is room 1. I can move back and forth. So that's why you have them connected back and forth. 3 to 4 also, I can move from 3 to 4. So that's why they are connected, 3 to 4 back and forth. Then 4 to 0 back and forth here. This is the door leading to 4 and 0. So I can move 4 and 0 back and forth. Also from 4 to 5, this is 4. I can exit here from 4, and anytime I'm outside this floor plan, I'm in 5 already. So 4 and 5 back and forth also. And to complete the matrix 5 to 5, that's why I have this 5 to 5. We see that in a minute, why that is necessary. So after I've converted it into a node map, the next thing is to assign rewards to the paths linking. So what I'm doing here is to assign maximum reward. In this case, I'm using 100. In most cases, we use 100 in Q-learning. 100 for paths that are leading directly to the destination, which is 5. And 0 for paths not leading to the destination in this case. So from 1 to 5 is 100. From 5 back to 1 is 0. From 5 to 5 is 100. From 4 to 5 is 100. And 5 to 4 is 0. From 3 to 4, 4 to 3 is 0, 0. 3 to 1, 1 to 3 is 0, 0 because they are not leading to the destination. 3 to 2 and 2 to 3 is 0, 0. And 0 to 4 and 4 to 0 is 0, 0. So after you have done that, the next thing is to form what we call the reward matrix. So your reward matrix R, how many states do we have? We have 0 to 5 states. All the nodes are your states. 0, 1, 2, 3, 4, 5. So 0, 1, 2, 3, 4, 5. And the action also will be 5 because you have to come up with a square matrix. So 5 actions, 0, 1, 2, 3, 4, 5. So state 0, action 0. Is it possible? You can't go from 0 to 0. So that is -1 because you can't go from 0 to 0. State 0, action 1. Can you go from 0 to 1? Is it possible? There's no link between 0 and 1. So it's -1. 0 and 2. There's no link between 0 and 2. That's -1. 0 and 3, there's no link. That's -1. 0 and 4, you can go from 0 to 4, but the reward is 0. So that's why you have 0 here. 0 to 5, there's no link. So it's -1. So for state 1, action 0. Can you move from 0 to 1? It's false. That's -1. 1, 1 also is -1. 1, 2, you can't go from 1 to 2. It's -1. But you can go from 1 to 3 and the reward is 0. 1 to 4 is impossible, is -1. But 1 to 5 is possible, is 100. So that's 100. So like that, you form the reward matrix as we have seen here. So after then, what you want to do is to form the brain of the robot, which is to form your Q matrix. So at the inception, so basically what you want to do with Q-learning is to fill the brain of the agent with the value or the reward for all its actions. So at this initial stage, the agent knows nothing about the environment. So that is why the Q matrix here is all having elements of zeros in this case, you know. So here you have the states 0 to 5, the action 0 to 5 as well, like you have in your reward matrix, but all the values are zeros to start with. Now, from the model of this Q learning algorithm, which is the Q state, actions equals R state, actions plus gamma times max Q into next state, all actions. That is the model the Q learning algorithm will use to build the brain of the robot. And this is how it's done. The procedure is listed here. Number 1, you set the gamma value and the environment reward in matrix R. So we have already done the environment reward in matrix R that we did here. Is what we call it copied back here. The gamma value, this gamma, we need to set it. Now in most cases, the gamma value you have is 0.8, 0.9, 0.7. The reason is this: the closer the gamma value is to 1, the more the weight of the Q for next state and all actions will be on the current Q value of the state, action that you're trying to evaluate. Because the more this gamma is closer to 1, the more the influence of this side of the model on the output you have here. So if this gamma is closer to 0, that means you are only getting the reward from the current state and action. But if your gamma is closer to 1, you're getting the reward also for all the next state and actions possible from where you are located in the environment at that point in time. So most cases you have gamma values between 0.7, 0.8, 0.9 in most cases that you have. So we initialize the matrix Q with all 0 elements. So that's what we have done here. We have initialized the matrix Q with all 0 elements. So we select a random initial state of the agent. So after we have done the Q matrix, initializing it with all values of 0, then we'll pick a location, a node, saying that that is where our agent is starting from. So we can either pick node 0, node 2, any of the nodes. So from that node, we'll now set the initial state as the current state of the agent. So whatever node we set will now be the initial state of the agent. So from there, we'll now select one of all possible actions for the current state. So from whatever state you have chosen, what are the all possible actions from that state? Saying that where can the agent go from that state that you are using as the current state. So using all the possible actions, we consider moving to the next state from that current state. Then we evaluate the maximum Q value for the next state based on all the possible actions. We compute the Q using the equation that we already had here. Then we repeat all of that until we get to the goal state. So this is what it's saying. For instance, if I choose node 1 as my initial state, which I'm picking at random, this is node 1. Now, from node 1, where can I possibly go from node 1? I can go from 1 to 5. I can go from 1 to 3. So here you have 3 and you have 5. However, I need to select one of all possible actions for the current state. So either I select 1 to 3 or 1 to 5. But in this case, I'm selecting 1 to 5. So using these possible actions, consider moving to the next state. So from 1 to 5, where can I go from 5? From 5, I can go back to 1. From 5, I can come back to 5. From 5, I can go to 4. So 1, 4, 5. So I'm selecting 1 to 5. Then from 5, I can go to 1 to 4 to 5. So using my model now, so I need to find the Q value for 1, 5. So that's what we have here. So Q 1, 5 equals R 1, 5. So what is R 1, 5? I will obtain that from this R matrix plus 0.8 is my gamma times max. So max into next state, all actions. So 5, 1, 5, 4, 5, 5. So that's what I have here. Q 5, 1, Q 5, 4, Q 5, 5. So Q next state, all actions. So what is R 1, 5? From here, R 1, 5 is 100. So that's why I have 100 here. Plus 0.8 is my gamma. What is Q 5, 1? From here is 0. 1, 5 is 0. Sorry, 5, 1. 5, 1 here is 0. 5, 4. 5, 4 is 0. 5, 5 is 0. So you have all zeros for this one. So that is 100 plus 8 times max. So the maximum value in this bracket is 0, because that's what this max is saying. The maximum value in this bracket is 0. So that's why it's 0.8 times 0. That will be 0. So Q1 comma 5 is 100. So now I know Q1 comma 5 to be 100. Then I will have to rewrite this Q table to fill in Q1 comma 5 to be 100, which is what has been done here. Q1 comma 5 is now 100. So from that again, I would select another state. In this case, here I'm selecting state 3 here. So from 3, I can go from 3 to 2, 3 to 1, 3 to 4. So if you look at it, 1, 2, 4. So I will choose one of these actions. So I'm choosing 3 to 1. So from 1, where can I go? 1 to 5, 1 back to 3. So 3 and 5. So Q3 comma 1 equals R3 comma 1 plus 0.8 times max Q1 comma 3 comma Q1 comma 5. So R3 comma 1, 3 comma 1 is 0 plus 0.8 times max Q1 comma 3 from here, Q1 comma 3 from here, because this is my updated Q now. Q1 comma 3 is 0. That's 0. Q1 comma 5, 1 comma 5 is 100. So it's 100. So the max value here is 100. So 0.8 times 100 will give you 80. So I'll rewrite my Q table again, my Q matrix again, to fill in 80 for Q1 comma 3, which is what we have done here. Q1 3 comma 1, 3 comma 1, 80. And our 100 that we got initially is equal here. So we'll keep doing that until we fill up all of these Q values. So that is how to fill the brain of the robot. So once that is done, the training is done, and the robot knows exactly how to take the best action in that case, because it now knows the reward for taking each of the actions. So I'll show how this is done in Python just for us to make sense of it. So here is the Q-learning algorithm in Python. So you import the libraries, the NumPy, the PyLab as PLT, then the network, so I can do my node structure of my network. So in this case, these are the possible points I have. So I can go from, so I have 0, 3, 3, 5, 3, 6, 0, 4, 4, 1, and 4, 2. And I'm saying that my goal is 1. So my matrix size here is 7 because I have 0 to 6 nodes. So my matrix size will be 7, 7 in this case. So these are just way of plotting my node structure of my map. So this is the node in this case. So it's saying 3 to 5, 3 to 6, 3 to 0, 0 to 4, 4 to 1, 4 to 2 is possible, and my goal is 1. So this is my reward matrix. Let's fill in them with -1. So later I did all my coding. Now I have my reward matrix here. So if you look at it, this is column 0, 1, 2, 3, 4, 5, 6 for actions. 0, 1, 2, 3, 4, 5, 6 for states. So this is 1, 2, 100. If we go back here, we'll see that state 0, 1, action 0, 1, 1, 2. So it's 100. Also 0, 1, 2, 3, 4, 0, 1, 2, 3, 4. So that will be 4, 1 is equally 100. So if you look at it, 4, 1, 4, 1 is 100. So that's my reward matrix, and this is my Q matrix. Initially is all zeros. So that is what my gamma here is 0.8 as well. My initial state I'm choosing that I'm on 1. So I'll build my Q matrix. So from there I got my trained Q matrix here, and I'm now saying my current state is 3. So if I'm on 3, how do I move to 1? If we go back to the network, the best way is from 3 to 0 to 4 to 1, because 1 is my goal state. So if you look at what the model is equally predicting, it's predicting that you go from 3, 0, 4 to 1. So that is the process in Python. So the limitation of machine learning is that machine learning cannot be applied to high-dimensional data. Now, what do we mean by high-dimensional data? If we look at how we have been discussing machine learning, we'll see that the programmer is responsible for knowing what the features the model should look at. From what we have done, we'll see that the programmer needs to know what should be my independent variable from this data that I have. But when it comes to high-dimensional data, particularly the problem of image recognition, handwriting recognition, voice recognition, those are problems that it's impossible for you to know what are the right features as a programmer to look at. For instance, if you have a friend, over time your friend will be speaking to you, you will know your friend's voice. And when you hear it anytime, you know that's the voice of your friend. Now, if one should ask you that how do you know it's your friend, you can't really tell the person that this is how you know, but you just know that that's your friend speaking. You understand? So you can't really tell what feature you are actually focusing on to know that that is your friend speaking. So in the same way, when it comes to such problems with AI, it's difficult to use machine learning approach because the programmer cannot by himself or herself, determine all the features to be looked into by the algorithm. So in that case, deep learning is the approach that will be used, because deep learning uses the artificial neural network, which is the same thing that the human brain has, which is a neural network that makes the human brain perform at that level to actually know how to focus on the right features by itself without being told that these are the right features. But the neurons by themselves learns to focus on the right features by themselves. So that's the method used in deep learning. So when it comes to problems of image recognition, problems of handwriting recognition or voice recognition, deep learning is the method that is being used. Now, deep learning and machine learning are two methods in AI that will solve data-driven problems. And from this image here, we can see that deep learning is subset to machine learning, while machine learning is subset to artificial intelligence. So deep learning is not an area by itself, but it's subset to machine learning, and machine learning is subset to artificial intelligence. So at this point, we'll close this lecture, and next time we'll be looking at deep learning. Thank you very much.